Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I am an assistant professor at Comsets University, Islamabad, WA campus. The topic of this lecture is addressing modes of 8086 microprocessor. These slides have been edited from the sources given here. To understand addressing modes used in Intel family of microprocessors and in particular an 8086 microprocessor, we need to understand what is a program and what are instructions in a program. A program is basically a set of instructions written by the programmers to solve a particular problem or to solve a specific problem. And instructions are then used to write a program. So an instruction is basically a direction which a microprocessor follows to execute a task or part of a task. So when a programmer wants to solve a problem by a computer, then the programmer has to give a set of instructions to the computer by writing set of instructions which forms a program. Just like natural languages, where an essay or a sentence is written by following set of rules to write English, for example, English sentence or English essay. Just like natural languages, computer programs can be written by following certain rules which are called programming languages. So computer language is a set of rule that guides the programmer to write programs or set of instructions to solve a problem by the computer. Programming languages or computer languages are divided into two types of languages: high-level languages and low-level languages. High-level languages include languages like Java, C++, and many other, while low-level languages are then further divided into machine language and assembly language. A machine language is the language that computer can understand, and in fact that is the only language that a computer can understand. In machine language, instructions are written in the binary bits, where zeros and ones represent a particular instruction, and then a program is a sequence of binary bits, and the sequence of bits include group of bits, where each group of bits represent a specific instruction. So a sequence of bits is a program in machine language, which the computer hardware then can execute it or can understand and then perform the particular task or solve a particular problem. Machine language programming in the machine language is very difficult because it is computer friendly or machine friendly, but it is difficult for the programmer to understand or to debug programs written in the machine language. So the other language that is easy for the human beings to understand is assembly language. Assembly language use English alphabets or mnemonics to write or to represent instructions in the machine language. It is easy for the programmers as compared to the machine language to understand and to remember. But the problem is that the computer machine doesn't understand programs in the assembly language. To do that, instructions or programs written in assembly language are then translated into machine language, to the bits in machine language. For this process, other programs are used to do this translation by the machine, and those programs are normally called assembler. The job of the assembler is to translate mnemonics or English alphabets to machine language instructions, which are then executed by the machine. To write programs in the assembly language, the programmer needs to understand different addressing modes, as every instruction of a program has to operate on some kind of data. To access data, there are different ways in which a source or destination operand is denoted in an instruction, and these different ways in which source or destination operand is denoted in an instruction are known as addressing modes. To understand different addressing modes, we will follow a simple assembly language instruction called move. Here, an instruction, a version of the move instruction is given here. The operation code or the opcode of this move instruction is MOV, and this instruction has two operands. One is the source operand and the other is the destination operand. The movement, the direction of the data movement is shown by this arrow. So this move instruction will transfer or will move 16-bit data in the BX register to AX register. So this BX register is the source of data, and this AX register is the destination of data. To better understand different addressing modes in assembly language instructions, we give a simple analogy. For example, if we need to understand or to find out where the microprocessor textbook is, then in this example, the addressing mode would be the different ways in which a source address of an item, for example the microprocessor textbook, is denoted are known as the addressing modes. Just like the microprocessor finds the data or the operands in the memory or in the register, different modes are there. Just like that, when we need to find a microprocessor textbook, we need some addressing modes. There are some addressing modes. For example, the address of the book may be told or denoted as here: shelf 1 in the main library of the University of XYZ. That is where the microprocessor textbook can be found. Another mode would be to write the same address on a piece of paper and enclose it in an envelope. So that is, this envelope has the address of the book. The third mode of the address would be the librarian will tell you the address. There can be a fourth mode: my assistant can tell who knows the address of the book. Mode 5, the address is mentioned in a letter in mailbox 2, and so on and so forth. So the address of the microprocessor textbook can be denoted in a number of ways, and all of these different ways are called the addressing modes. Just like that, we have the addressing modes. And 8086 microprocessor, these are the 12 addressing modes. These addressing modes are grouped. The first group of addressing modes include registers and immediate values or immediate data. The second mode involves memory data. In these modes, at least one of the operand is to be accessed from the memory. And the third group, the addressing modes, involve direct or indirect I/O port addressing, input and output port addressing. In the fourth group, there is relative addressing mode, and in the final group, there is an implied addressing mode. In the first group, there is register addressing mode. The instruction will specify the name of the register which holds the data to be operated on by the instruction. For example, this is an instruction move CL, DH. In this instruction, the content, the assembly language instruction include names of the register where to find the data. Here, the source of the data is a register and the destination of data is also a register. So this instruction moves the 8-bit content in the register DH to another register, to another 8-bit register CL, and both of these operands have been stored in the register and their names have been included in the instruction. So the operands or the address of the operands is by providing the names of the register where the data has to be accessed from. So this instruction include two registers. The source is a register, the destination is a register. So the data is directly accessed from the registers. So the data, the 8-bit data, moves from the DH register to the 8-bit CL register. In the microprocessor programming model, these are the registers. So we can locate register DH and register CL. This is the bus interface unit. These are the registers related to the bus interface unit. These are the registers in the execution unit. And this instruction will move the 8-bit data from DH register to an 8-bit CL register. Another addressing mode is immediate addressing mode. And an immediate addressing mode, an 8-bit or 16-bit data is specified as part of the instruction. So one operand is a register and another operand is an immediate 8-bit or 16-bit value. For example, move DL, 08H. So this instruction moves the 8-bit immediate data given here to the 8-bit register DL. That is, it stores the 08, which is an immediate 8-bit value, and stores it in the 8-bit DL register. This value 08H is an immediate data, and this is stored along with the instruction, where in the memory this instruction is stored. This immediate data is also stored as part of that instruction. Here a 16-bit data can be moved. Move X, 0A9FH. So this is a 16-bit hexadecimal value, immediate value. This is transferred to the 16-bit AX register. Note that in the immediate addressing mode, only the source operand can be immediate and not the destination. The assembly language instruction, for example, move 08H, DL is incorrect. But if the 08H is used as a source and DL is used as a destination, just like we did here, then this would be correct. But the immediate value cannot be used as a destination. In the second group of memory addressing modes, we need to understand how the physical address of the memory is calculated. In 8086 microprocessor, there are 20 address lines, and in 8086 microprocessor, these 20 address lines are sufficient to address 1 megabytes of memory. So that's why the maximum memory that 8086 can support is 1 megabytes of memory. However, the largest register in 8086 microprocessor is 16-bit, while the address lines or the address in 8086 memory is 20-bit. So this 20-bit address cannot be stored in 16-bit registers. For that, physical address will have to be calculated. A physical address is the actual address of a byte in the memory. It's a 20-bit address. So that's the value which goes out onto the address bus. The 20-bit address is the value which goes out onto the address bus. Memory address is normally represented in this form: segment colon offset, where the segment is a 16-bit segment number and offset is the 16-bit displacement value. For example, 89AB is the 16-bit value that would be taken from the segment register, while F012 is a 16-bit offset taken from any other 16-bit register. Each time the processor wants to access memory, it takes the contents of a segment register. For example, these are the segment registers, shifts the content of the segment register 1 hexadecimal place to the left, or it is equivalent to multiplying a 16 in the decimal, then adds the required offset to form the 20-bit address. So the 16-bit value in the segment register is left shifted by 1 hexadecimal place, and the offset value is added with this shifted segment number, which would give us 20-bit physical address. For example, if the memory address is represented in this format, where the 16-bit represents the segment number, the 16-bit value is the offset, then first the segment number, which is 89AB, is left shifted by 1 hexadecimal place, and that would mean a 0 is introduced at the right or least significant nibble position. The offset value, which is F012, is added with that value. This is a 20-bit value now. This offset is added, we will get 20-bit physical address or the absolute address 98AC2. This is 20-bit physical address in the memory where the byte of data has to be accessed. Now we are ready to understand memory addressing modes. The first addressing mode is the direct addressing. In this addressing mode, the effective address of the memory location at which the data operand is stored is given in the instruction. The effective address is just a 16-bit number written directly in the instruction. So here we have some examples. Move bx, 1354h enclosed in the bracket. This value is the effective address. This is a 16-bit effective address. The square brackets around the 1354h denotes the contents of the memory location. If there are no brackets, then this would be immediate addressing mode. The value is part of the instruction, but when brackets are used, then this would not be an immediate value, but it would be an effective address. When executed, this instruction will copy the contents of the memory location into BX register. So this is an effective address. At this address in the data segment, 16-bit content will be copied to the BX register. In this example, move BL, 0400H. The content, 16-bit content at this effective address in the data segment will be copied, not 16-bit but 8-bit content will be copied to the BL register. Why? Both of these are 16-bit effective addresses, but here the destination is a 16-bit register, while here the destination is an 8-bit register. So the amount of data, the size of the data to be transferred depends on the size of the destination here. This addressing mode is called direct because the displacement of the operand from the segment base is specified directly in the instruction. So this value is the effective address or the displacement from the starting address of the data segment. Remember that data segment is not mentioned here, but in this addressing mode, the data segment is the default segment. The data segment, the starting of the data segment is accessed by taking the 16-bit value from the data segment register, shifting left by 1 hexadecimal place, and adding this displacement with that value would give us the physical address from where 2 bytes of data has to be shifted to BX register in this example, and 1 byte has to be shifted to BL register. Another addressing mode, memory addressing mode, is register indirect addressing mode. And register indirect addressing, name of the register which holds the effective address will be specified in the instruction. Registers used to hold effective address are any of the following registers. These 4 registers, base pointer, destination index or source index which provide the effective address. Content of the data segment register is used for base address calculation. Just like in the previous mode, the data segment register is not mentioned here, but it is implicitly mentioned here. So what happens here? The 16-bit content from this effective address in the data segment register is transferred to the 16-bit CX register here. This is 16-bit register. So what happens when this instruction executes? The effective address is the content of register BX. The effective address is the 16-bit value stored in the BX register. That is the effective address. Then the base address of the segment is the 16-bit value of the data segment register shifted 1 hexadecimal place to the left or multiplying 16 in the decimal. This would give us a 20-bit base address. Then the memory address or the physical address is the sum of the 20-bit base address plus the 16-bit effective address which is stored in the BX register here. So here we would get the 20-bit memory address from where the 16-bit value is to be copied or transferred to the CX register. So we can write this like copy the 16-bit content from the memory address calculated here to the CX register, or in other words, the 1 byte value at this memory address is copied to the CL register, and then the memory address is automatically incremented by 1. So the next, or the byte in the upper memory address or the byte in the next memory address is copied to the higher part of the CX register, which is CH. And this format is called little endian, where the low byte in the memory is transferred to the low register and the high byte is transferred to the high register. Base addressing. In the base addressing mode, base register or base pointer register is used to hold the base value for effective address, and assign 8-bit or unsigned 16-bit displacement will be specified in the instruction. In case of 8-bit displacement, the displacement is sign extended to 16-bit before adding to the base value. When BX is used to store the base value of effective address, the 20-bit physical address is calculated from BX register and data segment register. But when the base value is stored in the base pointer register, then the effective address is calculated, the physical address is calculated from the base pointer and the stack segment register. So what here is an example: move AX, BX plus 08H. To calculate the physical address, the base address is stored in the base register. The displacement is provided here, 08H. First, this displacement value is sign extended to 16-bit value. Here, this displacement, 8-bit displacement in the hexadecimal, is sign extended to 16-bit value. The sign of the value is kept and it is extended to 16-bit. So that means sign extension to 16-bit. Then the effective address is calculated by adding the 16-bit value in the BX register. The 16-bit value in the BX register is the base address. This displacement sign extended displacement is added with the base, just like here. The 16-bit value in the base register plus sign extended displacement, both together will give the effective address. Then the base address, which is the starting address of the segment, is taken from the data segment. It is left shifted by 1 hexadecimal place, just like before. And both the starting address of the segment, which is base address, the effective address calculated here, would give us memory physical address, and then the 16-bit content from that memory address is copied to the accumulator, 16-bit accumulator register. This can be written as the following as well. The first byte at memory address calculated here is copied to the low part of the accumulator. The next byte is copied to the high part of accumulator. So in the base addressing, there is base register BX that provide the base value, and a displacement, an 8-bit or 16-bit displacement is added, and both are enclosed in the brackets. And this value, the sum of these two values, would give us the effective address, which is added with the base address of the segment. In this case, it is the data segment. And the 16-bit content from that physical address is then transferred to AX register. Index addressing. It is similar to base addressing mode, but it is different in providing the base value. In the base address, the base value is provided by the base register, BX register, while here the index is provided by the source index or destination index register. So, source index or destination index register is used to hold an index value for memory data, and just like base addressing, a signed 8-bit or unsigned 16-bit displacement will be specified inside the instruction. Displacement is added to the index value stored in these registers to obtain the effective address. In case of 8-bit displacement, just like base addressing, it is sign extended to 16-bit before adding to the base value. Here is an example. Move CX, comma, SI plus 0A2H enclosed in the brackets. So this value is sign extended to 16-bit value. This is the displacement. This displacement is added to the 16-bit index in the index register. This can be SI, it can be DI. The sum would give us effective address. This effective address is added with the data segment value, left shifted data segment value, which would give us the physical address or the memory address. Here are the operations. So this displacement A2H is sign extended. So the sign is 1 and that 1 is repeated. So to keep the sign, we would get this extended version FFA2 This sign extended displacement is added with the content of source index, and this addition would give us the effective address. So this part would give us the effective address, 16-bit effective address. This is the base address, which is the starting address of the segment, the data segment, is left shifted by one hexadecimal place, just like before. And the sum of this effective address plus base address would give us the memory address or the physical address. And the 16-bit content at this physical address is added to the CX register. Or in other words, the byte at this memory address is copied to the CL register, and the next byte is copied to the CH register. There are other addressing modes: base index, string, input and output, port addressing, relative, implied addressing modes. They would be discussed in the next part or second part of this lecture. If there are any queries while watching this lecture, please keep a note of those queries and you can ask them during the online session. Thank you.